In this question, we are looking for the Green's function for this differential equation. As before, we write down the homogeneous equation and find the general solution. The general solution in this case is a linear combination of sine and cosine terms. The Green's function is taken to be of a similar form where the constants are now functions of z. Just as before, the functions a, b, c, and d are to be determined using the three conditions that the Green's function has to satisfy. Firstly, the Green's function has to satisfy the boundary conditions. The first boundary condition is at x equals to 0, where the function has to be 0. This implies that a is equals to 0. The second boundary condition involves derivatives, so we first need to calculate the first derivative of g. The first derivative of x equals to 0 is also 0 according to the boundary conditions. This leads to the fact that b is equals to 0. With a and b 0, we update our expression for the Green's function. Now, before we continue with the remaining two conditions, it is convenient to redefine the functions c and d. So we let c and d to be expressed in terms of a new set of functions c tilde and d tilde. The reason for doing this is to simplify our Green's function. We shall see by substituting into the Green's function equation. And then we collect in terms of c tilde and d tilde. Then we observe that the functions in the brackets can be simplified using trigonometric identities. So the Green's function is reduced to this. We now resume to investigate the conditions. Next is the fact that g is continuous at x equals to z. This means that the top line and the bottom line must be equal to each other at x equals to z. So c is 0. Our Green's function is now left with one last function to be determined. We find d by the third condition. The first derivative jump at x equals to z. Hence we take the derivative of g. It must jump by 1, so we conclude that d is equals to 1 over omega. With this result, we can substitute in for our final expression for the Green's function.